says it right there, dipole. That's what we're doing. Dipoles, electrodynamics. There's a lot of tricks here, so buckle up. Let's get to it. I have here a dipole. So a dipole has a positive and a negative charge, and they're going to be separated by some distance d. What we want to do is to come up with an expression for both the electric potential and the electric field when we're further away. Now, if you want to start with something like the electric field on the axis of the dipole, that's a pretty easy derivation. And then also the electric field perpendicular to the dipole is very easy. I've done those before. I'm going to do the hard version of these. So let's get to it. So, we want to find the electric potential. Remember, the electric potential due to some point charge is 1 over 4 pi epsilon naught q over r. And r is the magnitude of the vector from the point charge to the observation location. Okay, so now I have 2 point charges, so the electric potential is just the sum of those the two potentials. Sum of the potential to this plus that. Okay, I have my dipole centered at the origin. So imagine that I have some vector r, RO, where I want to find the electric potential. So if with that I actually have 2 vectors, right? I have this vector, we'll call that r plus, and I have this vector r minus. So they're slightly different because the charges are not at the origin. So let's say the observation location RO is the vector x, y, z. I'm going to say r, I'm going to call it r. I'm trying to think of the position of this. Let's call it RQ1. RQ1. That's Q, that's 1 and that's 2. So RQ1 is going to be 0, 0, d over 2. RQ2 is going to be 0, 0, negative d over 2. So when I find R plus is going to be equal to the final position, RO, minus this position, so I get x, y, z minus d over 2. And then I get R minus is going to be x, y, z plus d over 2. Nothing's hard yet, right? That's pretty straightforward. Okay, so now we're going to have to find the magnitude of both of these vectors. So I'm just going to say r plus, the magnitude of that is going to be the square root of x squared plus y squared plus z minus d over 2 squared, right? Magnitude of vector, r minus, is the square root of x squared plus y squared plus z plus d over 2 quantity squared. Okay, now, and then I have the potential is just going to be q over 4 pi epsilon naught, and then I have 1 over r plus minus 1 over r minus. That's my potential, right? So that's my r plus, that's my r minus. It's kind of messy. So what I want to do now is to take just the r plus. Let's just do r plus. And let's see if we can simplify just that whole r plus thing. Okay, so if I take just r plus, I have an x squared, I have a y squared, and then I'm going to get a z squared in here. So let's just go ahead and multiply that out. So I'm going to write this r plus as the square root of x squared plus y squared plus z squared. And then I have this times this and this times this. So minus zd, I'm using those for z's because I have z's and 2's. And then plus d squared over 4. Now what I want to do is to, what do I want to do? Yeah, so this right here is r squared, right? So I can write this as r plus is the square root of r squared, x squared plus y squared plus z squared is r squared, minus zd plus d squared over 4. Now what I want to do is to factor out an r, right? So if I bring this r squared out, I get an r, but then I have to divide this by r squared and that by r squared. So I get r times the square root of 1 minus zd over r plus d squared over 4 r squared. Squared, right. And then if I multiply that in, I get the same thing. Okay, no tricks yet. Now I'm just double checking because I'm going to make a mistake. Yep. So now I want to rewrite this. I want to make the assumption that d is much less than r. So I want to make the claim that this is the same as 1 minus, so I'm going to say 1 minus zd over 2r squared is approximately equal to that. And you're thinking, well, that doesn't really make sense. Well, if this is equal to the square root of that, then this squared should be that. So let's square this, and I get 1 minus zd over r squared, right? Because I get 2 of those terms, r goes away. And then I get plus z squared d squared over 2r to the 4th. Now, if d is much less than r, then this term is very small. And so this is approximately, so then I take the square root of this and the square root of that. So this, and it's a trick. Let's trick meter up here. I'm going to put a little box. We're going to count our tricks. One trick. Okay, so now I have, let's just go back up here. I'm going to pull out my microphone. Be careful there. Okay. You would think I'd have a wireless microphone, but I don't. Okay, so I'm going to erase that. I'm going to erase this. So now I have r plus is going to be r times 1 minus zd over 2r squared. That's where I'm at right now. Now, if I do the same thing with r minus, let's switch over to r minus. Yeah, so r minus is the same thing, except I'm going to have a plus there instead of a minus, right? Because if I redid the whole problem, you could get that. And I know that, I guess I'll count that as another trick. It's a shortcut, but it's a trick. So minus, r minus is going to be r times 1 plus z d over 2r squared. So now let's put this in. V is q 4 pi epsilon naught, and then I have 1 over r plus, so I have 1 over, I can factor out, well, I'll do that. 1 over r times 1 minus z d over 2r squared minus 1 over r times 1 plus z d over 2r squared. Okay, I can factor out the 1 over r. I get q over 4 pi epsilon naught 1 over r 1 over 1 minus zd over 2r squared minus 1 over 1 plus zd over 2r squared. Now, another trick. So again, we're assuming d is really small. So imagine that I have 1, I'll put my trick over here, 1 over 1 plus epsilon. I'm going to say 1 is equal to 1 plus epsilon times 1 minus epsilon over 1 plus epsilon. So is that a good epsilon, some really small number? So if I do this, 1 plus epsilon times 1 minus epsilon is going to be 1 squared is 1. And then I'm going to get minus epsilon squared. So once you square a super small term, it's super duper small. So that means that this would be true, but that cancels, so I can write 1 over 1 plus epsilon as 1 minus epsilon. Trick. Okay, so that means that this is going to be equal to q over 4 pi epsilon naught 1 over r. So 1 minus this is the same as over is 1 plus 2d over 2r squared. And then I have minus 1 parentheses minus z d over 2r squared. All right, because I'd use the trick again. I don't really like that one, but that's fine. Okay, so now I get q over 4 pi epsilon naught. And then I have 1 minus 1 is 0. And then I have 2 minus a negative 2 is going to be, I'm going to get rid of the 2. So I'll just get z of 1 over r, 1 over r, z d over r squared. And that's my potential. Right? Yeah. Let's put that up here. So V is going to be Q. I'm going to put this as QZD over 4 pi epsilon naught r cubed. Double checking here. Yep. Okay, so now we're going to define the dipole moment. So, and that's not a trick, it's a definition. So let's define the dipole moment P as QD. So this is going to be the vector D from there to there. And so in this case, I can say the vector D is 0, 0, D. Now, if I have my observation location up here as R, X, Y, Z, and I take, so P, let's write it as a vector, is, well, that's fine, we can leave it like that. So QD dot R is going to be equal to, in this particular case, I get X times 0 plus Y times 0 plus Z times Q times D. That's what that is. So I can write this as P dot R over 4 pi epsilon naught r cubed. Now, you know, R, I can rewrite this as P dot R hat. R over R is R hat. So I'm going to take one of those R's and put it in with this, and I get R hat over 4 pi epsilon naught r squared. And that's my electric potential at any point. So it does depend on where you're at, right? Because I need to know the direction of my dipole. In this case, I had it in the z direction, and that's where that z comes in. So there's my electric potential as a function of r, with only 3 tricks. Is that right? Double checking, because I do make mistakes. Yep. Okay. Now let's find the electric field, and then we're going to plot it. Don't worry, we're going to plot it. Okay, so if I want to find the electric field, remember we defined the electric field as negative the gradient of the potential. And in this case, you know, you could write the potential, the gradient, in terms of Cartesian coordinates. But it seems like if this is my z direction and there's no change, nothing changes in the phi direction in the xy plane, so I can just describe this vector as some magnitude r and some angle theta. And in that case, I can write the gradient in just, I'll write it this way. It's going to be negative the partial of v with respect to r hat, minus the negative, 1 over r, the partial of v with respect to theta hat. Now that's only true because, remember, the partial, let's see, so phi doesn't matter. That's actually fine. Plus stuff, partial of v with respect to phi, which doesn't change, so that whole thing's 0. I guess that's a trick. Okay, so let's do negative. So I'm going to call this ER. It's going to be negative the partial of v with respect to r. So here's my v. Okay, up here, let's write this. In this case, P is in the z direction, right? So P dot r hat is just going to be equal to the magnitude of P times the magnitude of R, which is this R hat, which is 1, times the cosine of the angle between those two, which is going to be theta. So then that's going to be 4 pi epsilon naught R squared. So I'm going to take the, I'm going to keep theta constant. and I'm going to take the partial with respect to r, so I'm going to get -2, which is there's another negative there, so I get 2p cosine theta over 4 pi epsilon naught r cubed, right? So when I take the derivative, it's r to the -2. I bring the -2 down front. I decrease by 1. I get -3. That's that. E theta is going to be equal to -1 over r times the partial of this with respect to theta. The derivative of cosine theta with respect to theta is negative sine. Boom. So I get p sine theta 4 pi epsilon naught r squared. So this is going to be equal to p sine theta over 4 pi epsilon naught r cubed. So there I have my electric field in the r direction and in the theta direction. And then I have my electric potential as a function of r. Now this is going to be important because the whole point of looking at a dipole is with what we call multipole expansion, which is to represent different charge distributions as though they were just a dipole. And we'll do that later. Okay, but we have to understand how to represent a dipole first. I think what we need to do now is to make a visual of this. So what I'm going to do is I'm going to make a plot, a diagram of the electric field for a dipole. Okay, so there's two ways I can do that. The first way is this. Now this way uses some tricks. So it's not absolutely correct, right? So if I have r very close to d, then it's very not true, but it's approximately true. The other way to do this is just to find the electric field due to these two charges and just add them up. Okay, so I'm going to do that in Python. So let's just start. I'm going to start with just two charges. I'm going to find the electric field due to each one. I'm going to use Cartesian coordinates. I'm just going to brute force it. And then we'll display the arrows at different points around the dipole. And we'll do that in VPython. And then I'll come back and I'll talk about how we do this. Okay, so switching over here to VPython, Web VPython. I have my, I need some constants here. So let's say k is equal to 1. That's my 1 over 4 pi epsilon naught. I don't have to deal with that. Q is equal to 1, again, because I just don't really care. And then D, I want that to be 0. I'm going to put 0.01. So I just pick a small number. It doesn't really matter. It just matters in terms of that number. Okay. So I'm going to give a vector location for the two charges. So let's say QP is going to be the vector 0. I'm going to do this in the y direction instead of the z direction because in Python z is out of the page and it doesn't look that great. So it's going to be d over 2, 0, and then qm for q minus is going to be, I'm not going to draw those, they're just dots, 0, negative d over 2, 0. Now, what I want to do is I want to be able to calculate the electric field anywhere. So I'm going to actually make a function for the electric field absolute. So I'm going to call this, I'm going to say def E1, because I'm going to have an E2. So E1, all I'm going to do is pass to it an observation location. So I'm going to call it ROT. So pass a vector to it, and it should give me back a vector for the electric field. The first thing I want to do is to calculate RP. RP is going to be ROT minus QP, right? So that's the vector from the positive charge to whatever vector observation location I give it. And then Rm is going to be ROT minus Qm. Now I can calculate the total electric field. I'll do this as a temporary vector. It's going to be K times Q times 1, it's going to be norm Rp divided by mag Rp squared. So remember, this is the electric field due to a single point charge. It's KQ r hat over r squared. So that's r hat right there, and that's r squared. Now I need to do it for the negative term, but remember, I already factored out the q, so I'm going to say minus right there. Norm Rm divided by mag Rm squared. And then I'm going to return, oh, you can't even see that. But you knew what it was. You don't just pretend like you didn't know what it was. I knew you knew what it was. Okay, return ET. Let's just test it. So let's just see if this works. Print E1 vector 0.5, oops, 0.5, 0.05, 0.05, 0. Let's just see if it gives me a number. It should be a vector. And it didn't. See, I made a mistake. Missing a right parentheses. This is why we test stuff. Line 15, missing a right parentheses. Norm, mag, where am I missing that? Okay, so there's that. Missing a right parentheses. K, maybe I missed it up here. Okay. Oh, that's right there. Because I called it a function. No. Missing a right parentheses. Okay, norm that minus norm. I'm not missing a right parentheses, am I? K times Q times parentheses norm RP divided by mag RP squared, that's fine, minus norm RM minus mag RM quantity squared. Where am I missing the right parentheses? Well, let's just try this. That should be fine. Oh, I'm missing it down here. Vector, that's where I was missing it. Okay, let's put that back in. Oops. I'm just bumbling around like an idiot. Okay, so E1 vector, and then that's for E1, and then I have to have a print. That was dumb. No? Too many right parentheses in line 11. This is silly. I can't possibly be missing it. And you probably see it. You're like, what the heck, guy, man? Look at what you're doing. Okay, so let's just go back to my original plan. Oh, that one I did. That one I did. And now I have this. I'm making errors by fixing errors. Got it. Boom! Whew. I felt dumb for a second there. Okay, so now what I want to do is to make arrows there. Notice that the magnitude here is in the 40s. So I want to make arrows for this. So let's just put a sphere at the origin just so it looks cool. Sphere is position vector 0, 0, 0. Radius is going to be 0.002. That's fine. And now what I want to do, I'm going to say theta is equal to 0. D theta is equal to 2 times pi divided by 10. So what I want to do is to move around in a circle and plot the electric field. So while theta is less than 2 times pi, what I'm going to do is to move, I'm going to have an observation location and move it around. So let's say RO, I want to make a radius of this circle. Let's say the radius is equal to 0.03. RO is the vector, it's going to be R, times the vector cosine theta. I'm using this in the XY plane, so don't confuse this with the theta from up there. Sine theta, spell it right, 0. Now I want to make an arrow there using that observation location. So arrow, POS is RO. Axis is going to be equal to E scale, which I haven't put. Let's put that right here. E scale is 1 over 100. Probably need to be smaller than that, but that's fine. E scale times E1 of RO. So I'm going to pass that location to my function. It will give me back the electric field vector, and then I'm going to use that to make an arrow. And let's make this yellow. Color equals color dot yellow. Okay, so now I need to move my angle theta. Theta is theta plus d theta. Let's run this thing. Okay, too big. So it seems like I don't have enough arrows either. Theta is 2 pi. Well, that's fine. So E scale, let's just add a couple zeros there. Okay, still too big. So I'm just going to write this in scientific notation. 1e negative 7 too small. 1e negative 6. Too small. 1e negative 5. And that's going to be just right. There we go. Dipole. Okay, so that's my dipole. It's only 1 point. And then remember, it's in the plus y direction, so it curves around like that. That's exactly what we would expect. Pretty happy with that. So now what I want to do is to plot the calculation that we had before. So we're going to give it an r value and a theta value. But that's measured from now the y-axis, not the z-axis. And then in order to plot the arrow, if I give it a y, an r and a theta, how am I going to get back to Cartesian? Because VPython uses Cartesian coordinates. Let's just jump over here and let's draw a picture so that we can know what's going on on the board. Okay. So we're going to use this for ER, this for E theta. So we need to calculate P. But now let's just imagine that I have, let's call that the y-axis, and then here's my P vector. So I have P is like that, and then I'm over here. So that's R, and that's theta. And I'm going to calculate ER r hat, and then E theta theta hat. But as I move around, r hat and theta hat change, and I need to get r hat and theta hat in terms of Cartesian coordinates. So here, and there's better ways to do this, but I'm doing this the simple way. So here you can see that this angle right there is the same as that angle right there. Right? Yeah, so if this goes up, no, this angle is the same. So here I'm going to write r hat as the vector sine of theta cosine of theta 0. So the x component is going to be the opposite side of that right triangle, so that's sine of theta. And then the y component is going to be cosine theta, which is wrong the way you normally do it. But remember, we're defining theta from that vertical axis. So that's why I'm going to do that. And so once I calculate, well, let's write it in a second. So theta hat is going to be equal to, now we're in this direction, right? So this is, okay, if that's theta, this is theta. So this is going to be equal to cosine theta in the x direction, and then negative sine theta in the y direction. So if you use normal Cartesian coordinates, those things are flipped, okay? But we're not. We're measuring from the y-axis, not the x-axis. And then I can write the vector E. Now that I have those in Cartesian coordinates, that's x, y, z, x, y, z. I can write E as ER r hat plus E theta theta hat. And then ER is this, and E theta is that. Okay. I know it's a lot of work, but we're going to do it anyway. Switching back to WebVPython. So I'm going to make a new function here called E2. And E2 is going to calculate the electric field using the other way. So def E2 ROT. And so the first thing I need is P. So P is going to be equal to Q times D in this version. I've already taken into account the direction of this. I don't have to do the R dot and things like that. Although I could. Whatever. OK. So let's say I'm going to calculate. I need to calculate R. I need to calculate theta. So that's the first thing. So R is going to be equal to the magnitude of ROT. Right? That's the magnitude of the observation location. Now, theta, I'm going to call it theta t for temporary theta. It's going to be equal to, I should have drawn this up here. If I use the opposite side of this right triangle as my x and my adjacent side is sine, it's y. So this is going to be arctangent, a tangent of x. So ROT dot x divided by ROT dot y. So now I have my angles. So now I have r and theta. Next thing I need is my r hat. So r hat is going to be the vector sine theta cosine theta 0. And then I need my theta hat. Theta hat is going to be equal to vector. Doesn't say which one was negative. Okay, so it's cosine theta, oops, t, cosine theta t, negative sine theta t, 0. Okay, now I can calculate ER. ER is going to be equal to this thing right here. So it's 2 times P times cosine theta t divided by, oh, there's a K. K, that's a 1 over 4 pi, divided by R cubed. So R, and then E theta is going to be equal to P times K times sine theta divided by R cubed. And then I'm going to return the vector ER times R hat, which is a vector, plus E theta times theta hat. And it's done. I should test that, shouldn't I? No, I'm not going to. I'm just going to do it. Okay, so now I'm going to make a second arrow down here. Arrow, POS equals RO. Axis is going to be E scale times E2 RO, right? So I'm using the other method to calculate this one. And let's make it a different color. Color equals color dot magenta. And that should do it. We should be done. Let's run it. Something happened. Cannot add a vector and a scalar. Okay, what did I do wrong? Cannot add ER, E theta. Oh, that was a simple mistake. Okay, so there you go. You can see that there is some difference in these vectors. You see that? But they're very, very similar. They're very, very close. Let's move our R in closer and see if we can get a different result. So up here, I'm going to, instead of using R at 0.03, let's just do it at 0.02. Now, I'm probably going to have to make my scale smaller because my fields are going to be bigger. But that's okay. You see now the two electric fields do not completely agree, right? So now they're off a little bit and they're shorter, different little bit. They're not the same thing. So it's not the best approximation to say that what we did when we said that D was much less than R, that's no longer the case. Okay, so you can make the vector smaller, but you get the point. Okay, if you want this code, I'll put a link to it down below. But the next thing we're going to do is to make approximation for charge distributions using the dipole expansion. The end.